To help illustrate how the cross-entropy loss works for multiple classes, let's actually take a look at some concrete code examples where we plug in some actual values. So just a brief recap of what we've covered in the previous part. So we talked about the two summation terms where we have one summation term going over the training examples and the second summation term going over the multiple class labels. Then we learned about the one-hot encoding, and we learned that we need this one-hot encoding to plug into the value of y here. So the y here stands for the class label that we need in the one-hot encoded form. And then we talked about how we can convert an integer class label array into this one-hot encoded form. So here assume we have this integer array 0, 2, 2, and 1. So we have 3 class labels. And then we have on the right-hand side the corresponding one-hot encoded form. So in the next couple of slides, I will walk you through how we actually do the one-hot encoding and the loss computation with some actual numbers and code. So let's start by converting the integer labels into this one-hot encoded form. So for that, we are going to use the one-hot function implemented in PyTorch. And now suppose we have the net input values corresponding to the 4 training examples. These are the values computed by our softmax regression model. So here the 4 rows correspond to the 4 training examples, and the 3 columns correspond to the 3 labels 0, 1, and 2. Then, as we saw earlier, we convert these net inputs into the class membership probabilities using the softmax activation function. So here we are using dim equal to 1, dimension equal to 1 to make sure that the softmax function is applied such that all the values in one row sum up to 1. If we would replace this value by dim equals 0, what would happen is that all the columns, all the values in one column, would sum up to 1, which is not what we want. Like we learned before, what we want is that for each row, for each training example, all the class membership probabilities should sum up to 1. So here's an illustration to just make sure we know where we are, because sometimes we can easily get lost in the details. So each row here, each training example has these 3 class membership probability values, and they will map to the architecture here on the right as follows, as we've seen earlier. Yeah, now let's move along and compute the actual loss for our training examples. So we will start with the first training example. So we are only looking at the inner summation term here. So the inner summation is again over the class labels. Here are the 3 values in that row. And since we know that the class label is 0, we have the one-hot encoded labels 1, 0, 0. Yeah, let's now take these class membership probabilities and the one-hot encoded values and put that into the loss function. So for the first pair, we have -1 times log of the activation. And for the second pair, we have -0 times log of the activation. And for the third pair, we have again -0 times log of the activation. And you know 0 times something is 0. So the only part we have to pay attention to is the first one, -1 times log times activation. And that's going to be the loss for this particular training example. And then we do exactly the same thing for the second training example. However, now since this is a training example corresponding to class 2, the -1 here is at the third, at the last index position. Yeah, and we repeat exactly the same thing for training example 3. And then we have lastly training example 4, where the one-hot encoded label is in the second position. So here we have -1 times log of the activation in the second position. So yeah, what we have done now is we computed the inner terms for each of the training examples. Now it's time to get to the outer sum where we sum over these training examples. Notice that we also have this normalization term 1 over n here. So in this case, since we have 4 training examples, we have 1 over 4 times the sum of these individual loss terms as our total loss for this dataset. And yeah, this is how we compute the cross-entropy loss. So now that we are somewhat familiar of how the cross-entropy loss works, how can we actually implement that in PyTorch? Yeah, it's actually not too complicated. We start with the activation. So first we compute the softmax activations, and then we convert our class label array into this one-hot encoded form. Then we compute the individual losses with a sum over the training examples, which is exactly what we have done in the previous slides. And then, yeah, we compute the average, the normalization over the number of training examples. Yeah, and so this is one way we can implement a cross-entropy loss in PyTorch. And since the cross-entropy loss is such a commonly used function, the PyTorch team already implements a version of that internally in PyTorch for us. However, in the PyTorch version of the cross-entropy loss here, there are a few little differences. So the way we implemented this cross-entropy in the previous slide, we don't need to manually do the one-hot encoding before we pass it into the function. And similarly, we also don't need to apply the softmax step outside the cross-entropy function. So the cross-entropy function itself takes care of the one-hot encoding and the softmax activations internally. And this is also how it's implemented in the official PyTorch version of the cross-entropy loss, which we can see here. What's worth highlighting again is that we pass in the net inputs directly. We don't need to do the one-hot encoding, and we don't need to do the softmax activations because the PyTorch loss here takes care of it for us. Alright, so in this video we discussed how we compute the cross-entropy loss. So with that, we finished the topic of softmax regression, and we can actually take these concepts now that we just learned about and apply them to multi-layer neural networks, which is what we came here to learn about in the first place. So in the next video, we will talk about multi-layer neural networks.